Okay, I'm going to finish up this proof. Ran out of video on the last one. So likewise in number 4, we have a part in that we need to add to another part to equal a whole. So the part right next to in is ai, and together in and ai make an. Now we've already written our final statement, but let's make sure that we understand why the substitution property was used to get there. So you can see all these little arrows out to the side. You don't have to make these when you make a proof. They're just showing you that to get to number 5, you're using numbers 2, 3, and 4 to get there. That's what you're doing the substitution with. So in number 2, we said LA and AI add to equal IN and AI added together. So since these two things are equal, remember we can replace anything with something that is also equal to it. Well, what do we know that is equal to LA plus AI? LA plus AI is equal to LI. So I can replace this side of the equation with LI, and that's where this comes from in number 5. And on the right side, IN plus AI, we know AN plus AI is equal to AN. So I can replace this side of the equation with AN. So that's why the substitution property is listed for the reason for our final statement. So just one final note about proofs. I've already told you that when you're given a statement, that when you put that into your proof, your reason for it is just simply that you were given. You never put as your final step, the reason for it is prove. That does not make sense. You have to have a reason for that final step. So you will never use the word prove as a reason. That would never ever make sense. So numbers 9 and 10 in our notes are a proof of a new theorem that is called the common segment theorem. Now, it's called the common segment theorem because it's using a segment that two have in common. So given this, we proved it in 2 different ways in numbers 9 and 10. If you look at the first statement, it says if AC, which is this whole distance, equals BD, this whole distance, what do they have in common? Well, this segment and this segment have this distance B to C in common. So this segment, being the part that's in common, means the parts that they each had individually have to be equal to each other. So if AC is equal to BD, since they share this part in common, that means this part, AB, has to equal this part, CD. The other statement is simply what we call the converse of the original one. It's where you switch the if and the then part. So now it says if this is true, AB equals CD, our then part is going to be this part being true, that AC equals BD. So it is true both ways. If you know AC is equal to BD, then AB and CD equal. And if you know AB and CD equal, then you can add that common segment to each one of them and still end up with equal measures, A to C, B to D. So again, that's called the common segment theorem because this is the segment that they have in common. Make sure you keep this notes for lesson 4.2. You're going to need it when we get to lesson 4.4.